So this chapter is about normal distributions and standard z-scores. So this section is about finding scores. And instead of trying to find the proportion like we did before in the other sections, we're going to try to find the score based on the proportion. And the first example shows how to find one score. So the first step is to sketch a normal curve, and on the correct side of the mean, draw a line representing the target score. So in this situation, the target score is the point along the base of the curve that splits the total area into 80% to the left and 20% to the right. And the next step is plan your solution according to the normal table. Because the target score is on the right side of the mean, concentrate on the area in the upper half of the normal curve as described in columns B and C. The next step is to find Z. So we refer to table A. We scan column C to find 0.2000. If it doesn't appear in column C, which it doesn't, we find the entry in column C nearest to 0.2000, so that would be 0.2005. And the corresponding z-score for that is 0.84. So basically what that means is that the z-score of 0.84 is the point that separates the upper 20% of the area from the rest of the area under the normal curve. So then we convert z to the target score, and it gives us the equation right there. So we convert the z-score of 0.84 into an exam score, given a distribution with a mean of 230 and a standard deviation of 50. The target score must be located at 0.84 of a standard deviation above its mean. The distance of the target score above its mean equals 42, which, when added to a mean of 230, yields a value of 272. Therefore, 272 is the lowest score in the exam that receives an A. And there's just a reminder that a z-score indicates how many standard deviations the original score is above or below the mean. And then we have an example for finding two scores. And our example is that the annual rainfall in San Francisco approximates a normal curve with a mean of 22 inches and a standard deviation of 4 inches. And it asks what are the rainfalls for the more atypical years, defined as the driest 2.5% of all years and the wettest 2.5% of all years. So step one is to sketch a normal curve on either side of the mean. Draw two lines representing the target scores. The smaller and driest target score splits the total area into 0.0250 to the left and 0.9750 to the right, and the larger or wettest target score does the exact opposite. So then you plan your solution according to the normal curve. Since the smaller target score is located on the lower side of the mean, we concentrate on the area in the lower half of the normal curve. As described in columns B and C, the target z-score can be found by scanning either column B for 0.4750 or column C for 0.0350. After finding the smaller target score, we show the symmetrical properties of normal curves in order to find the value of the larger. The next step is to find Z. We scan column B for 0.475 or the entry nearest to 0.475 since it does appear in column B, with the corresponding z-score in column A equaling negative 1.96. The same z-score would be obtained if column C had been searched for a value of 0.0250. So we convert Z to the target score, and we find that The target score equals 14.16 inches, the annual amount of rainfall that separates the wettest 2.5% of all years from all other years. And there's just some more information about z-scores. So z-scores can be applied to any type of distribution, regardless of the shape of the distribution. The shift to z-scores always produces a distribution of standard scores with a mean of 0 and a standard deviation of 1. The use of z-scores can help you identify a person's relative strengths and weaknesses on several different tests. Z-scores reflect performance relative to some group rather than an absolute standard. A meaningful interpretation of z-scores requires that the nature of the reference group be specified. Standard scores are any unit-free scores expressed relative to a known mean and a known standard deviation. Although z-scores qualify as standard scores because they are unit-free and expressed relative to a known mean of 0 and a known standard deviation of 1, other scores also qualify as standard scores. Then transformed standard scores are a standard score that, unlike a z-score, usually lacks negative signs and decimal points, so it can be particularly used when test results are being reported to a wide audience, and also a z-score can be converted to a transformed standard score to make things easier.